So in the earlier lecture I talked about homogeneity of space. Now I will talk about isotropy of space, and the consequence of this is the law of conservation of angular momentum. So let us discuss that. What is the meaning of isotropy of space? Isotropy of space means there is no preferred direction in space. In space, or in other words, we can say that isotropic space has rotational invariance. Isotropic space has a rotational invariance, means any law of physics will remain unchanged when the space will be rotated, right? So we will take the example of the potential energy between two particles. Between two particles, right? We will start with this here. So let us proceed as follows. So consider two particles in this one stationary frame. Say there is a stationary frame. So this is a stationary frame. Say it is x-axis, it is y-axis, and say it is z-axis, and there is a one point located at this point, and there is another point which is located at another point. Say that point will be, say this point is x1, say this is one point and represented by point A, and its coordinates are x1 and the y1, and there is another point V, its coordinates are the x2 and the y2. So now we are having another frame, say let us say it is a S frame, and we are having another frame S prime which is rotated about xy plane. When the new frame is rotated about x-axis, or say it is x prime, and say it is, just a minute, yeah, so this is it. So it is x prime and it is y prime, and it is rotated about z axis, then z and the z prime axis both will remain the same, and say it is rotated through an angle d theta. Now first of all, let us consider the 2 points A represented by x1, y1, and another point is B, and it is represented by x2 and y2, and these are the 2 points represented in S frame. And now the potential energy between these 2 points is represented by U, and which is a function of x1, y1, x2 and y2. The potential energy between two particles which are located at A and B is represented by this in S frame. Now we have also considered another frame. That frame of reference is S prime, and this frame is obtained by rotating a xy plane about z axis through angle, it is z axis, not z prime axis, through small angle d theta, right? So this is it. Now there is another problem which is there. Now we want to relate the points x1, y1, x2 and y2, and how these are related to x1 prime, x2 prime, sorry, x1 prime, y1 prime, x2 prime and y2 prime. Now we want to relate these 2 points, right? So as we have discussed in the earlier lecture that if I recall that earlier lectures, say if we are having a so say it is x-axis and it is y-axis and it is x prime axis, and say it is y prime axis, and there is a some point and it is represented by x and y in one frame of reference. In another frame of reference this is represented by x prime and a y prime. So how these are related, as we have discussed in the earlier lecture, that let me discuss this. First of all, we have discussed that x prime is equal to x cos theta plus y sin theta, and similarly y prime is represented by x sin theta plus y cos of theta. As we know that, and say it is rotated about this, but in this case which we have considered here, that the theta is small, infinite is small, and it is represented by d theta. So in place of theta we can place d theta. So what will happen, this x prime will become x cos of d theta plus y sin of d theta, and y prime is represented by minus x sin d theta plus y cos of d theta. So this is represented by this one. But d theta approaches to 0. What does it mean? If d theta approaches to 0, then sine of d theta is nearly equal to d theta and cos of d theta is nearly equal to 1. This is small result, standard result. So if I use this result, then what this x prime will become? X prime will become x plus y d theta, and y prime will become minus x d theta plus y, or it is represented by y minus x d theta. This is the result which we have to remember. So, but we are not having a 1 point, we are having 2 points here, x1 and y2, y1, and how these points are related to one another. Using this result, I can write down it as this x1 prime is equal to x1 plus y1 d theta, and y1 prime can be represented by minus x d theta, x1 d theta plus y1, or sometimes it is represented by, in some texts like this. And for the second point, it is represented by x2 prime. It is x2 plus y2 d theta, and similarly y2 prime represented by minus x2 d theta plus y2, or it can also be written as y2 minus x2 d theta. So this is the transformation, means this is the relationship between these 2 points in S and the S prime frame. Now the potential energy this is the potential energy in S frame. Now potential energy of these particles in S prime frame is represented by U is equal to U x1 prime, y1 prime, x2 prime and y2 prime. But what is the meaning of isotropy of space? Isotropy of space means the potential energy between two frames will remain the same, or in other words we can say that the isotropy of leads to state that this potential energy will remain the same, or potential energy what does it mean? That means this potential energy is independent of rotation of coordinate system. Right? So let me use this result. Go to the new page. Yeah. So this is the result which we will use here. And isotropy of space leads to state that u x1 prime y1 prime x2 prime y2 prime is equal to u x1 y1 x2 and y2, means this potential energy will remain the same. But if I put these values from here, then how this can be written as? This potential energy can be written as it is x1 plus y d theta, comma y1 x1 d theta, comma x2 plus y2 d theta, comma y2 minus x2 d theta is equal to u x1 y1 x2 and y2. I use these results here, and if I can apply Taylor theorem over this part, so applying Taylor theorem, so how left hand side can be written as? This left hand side can be written as applying Taylor's theorem. Here I discussed Taylor's theorem in the early lecture, so it is x1 y1 x2 y2 plus by d theta, sorry, it is y1, so it is y1 d theta and partial derivative of this with respect to this parameter, curly x1 plus, not plus but the minus is here, this second value, minus x d theta and curly u over x1, it is x1 d theta, let me write down it again, yeah, minus x1 d theta curly u over curly y1, means derivative with respect to this one, this parameter, plus this y2 d theta curly u over curly x2, derivative with respect to this, plus, not plus but the minus, and this minus x2 d theta, and it is curly u over curly y2. This is it. As we know that f of x plus h can be written as nearly equal to f of x plus h into derivative of f with respect to x. But here more than one variables are there, dependence upon more than one variables, so that's why we have to write down it in this way. In place of h, here h is sitting here, this is also difference, small difference, slight difference, and like this, right? So I'm just generalizing these results, and this left hand side can be expanded to this one, but this left hand side is equal to this one. So I applied Taylor's theorem here, means this, and this is equal to u x1 y1 x2 and the y2, both will equal and opposite, or both are equal and lying on the opposite side, so both will cancel out, and d theta is sitting here, here, here and here, so let us take it outside, so it will remain d theta, it is y1 curly u over curly x1 minus x1 curly u over curly y1 plus y2 curly u over curly x2 and minus x2 curly u over curly y2, and this is equal to 0. As we know that d theta is not equal to 0, so that means this part is equal to 0. So let me write it down. So that means this y1 curly u over curly x1 minus x1 curly u over curly y1 plus y2 curly u over curly x2 minus x2 curly u over curly y2, this is equal to 0, right? But this is the potential gradient. So if we recall, potential gradient, this leads to the force. Gradient is basically nothing but it is a force, negative of the potential gradient. So therefore minus curly u over curly x1, what is it? It is the partial derivative of potential energy with respect to x1. So that means it is force on the first particle, and it is its first x component. So that means what is it? It is basically x component of force on particle 1 which is at position A. And similarly I can write down curly u over curly y1, it is basically f1y and it represents y component of force on particle 1 at A, because force has two components. Similarly curly u over curly x1, sorry, curly x2 is basically f of 2x, it is the x component of force on particle 2 at position B, and similarly curly u over curly y2 is equal to f of 2y, it is y component of force on particle 2 at B, right? This is it. So this equation can be written as this part. This part can be written as minus y1. This part can be written as minus y1 f1x plus x1 f1y minus y2 f2x plus x2 f2y is equal to 0. Let me rewrite down this equation now. So how this can be written as, it is x1 f1y minus y1 f1x, this plus x2 f2y minus y2 f of 2x, and this is equal to 0. So what is this? This is the force, and as we know that force is the rate of change of momentum. So if this is rate of change of momentum, then how this can be written as, this is x1 dp1 by over dt minus y1 dp1x over dt plus x2 dp2y over dt minus y2 dp2x over dt, this is equal to 0. let us now try to look at this part. So what is it? It is x1 dp1y over dt minus y1 dp1 x over dt. I'm just considering this part. And let us do one thing. Let us take its derivative x1. So this can be written as, say, x1 dp1y over dt minus y1 dp1x over dt. Let us take its derivative. So its derivative can be written as dx1 over dt, and let us put this term as it is. So p1y. If I am adding this term, so let us subtract this term again. That means equality does not disturb. It is p1y. And what is p1y? If I try to look at p1y, what is p1y? This p1y is equal to mass of the particle. Say if m1 is the mass of the particle, and this is written as the velocity v1y, or it is m1 dp1y over dt. So it can be written in this way. Sorry, dx1y, sorry, dx1. No, sorry. It is dx1. Yeah. It can be written as d, it is y, so it is dy1. Right? So let us do one thing. Let me rearrange this part. It will remain as it is. And how this part can be written? If I put its value this way, so that means dx1 over dt into m1 dy1 over dt. It can also be written as dy1 over dt m1 dx1 over dt, and this is nothing but this part can be written as dy1 over dt into p1x. That means this part can be written as this is equal to dy1 over dt plus p1x. It is p1x. So therefore this equation can be rewritten as x1 dp1 over dt. With this I am putting this equation, this with this, so it is plus dx1 dt and p1y, and minus sign can be taken outside here, so inside it is y1 dp1x over dt, and this term is equated this one, so it is plus dy1 over dt and d1x. Right? So what is it? This is basically type of product rule. So therefore it is written as d upon dt. It is basically d upon dt x1 p1y minus, this can be written as y1 and p1x, its derivative. It can be written in this way. So therefore this will become like this: x1 p1y minus y1 p1x. It can be written this way, right? And this whole of the term is equal to 0. Yeah, so this can be written in this way. Yeah. So this part is equal to this one. Let me go back. Yeah. Now it's better. So therefore, this particular term is equal to this one. So I can write down it as d upon dt x1 p1y minus y1 p1x. And similarly, I can write down this another part as the d upon dt of x2 p2y minus y1 p2x. It can be written in this way, and this is equal to 0. And if, let me now recall another very important thing, that is the angular momentum. And as we know that angular momentum is defined as L is equal to R cross P. This L is equal to R cross P. We have studied it in the +2 level. So what is R? It is I cap, it is J cap, it is K cap, X, Y, Z. It is Px, Py and Pz. And if I solve this determinant, this what it gives us? It's Ypz minus Zpy I cap minus J cap. It is minus of this, for this it is Zpx minus xpz j cap, plus it will be for the z component, it is xpy minus ypx. It is k cap. So if I try to look at that, this is the Lz component, this is Lx component, and it is the Ly component. So if I try to look at, it is the z component of angular momentum for the first particle, and it is the z component of second particle. So it is L1z and L2z. So therefore, this equation can be written as d upon dt of L1z plus d upon dt of L2z is equal to 0. So let me put these two together, L1z and L2z. It is equal to 0, and say their net is represented by Lz. It is equal to 0. So what does it mean? If the derivative of angular momentum means derivative of z component, say here, derivative of z component of total angular momentum, that is Lz, is equal to 0, this implies that this quantity will be constant. Then and only then derivative will be 0. So that means z component will be constant. Similarly, we can prove that Lx, Ly both are constant. Thus we can say that total angular momentum is constant, and this we have obtained by considering isotropy of space. So thus consequence of isotropy of space is thus consequence of isotropy of space is conservation of total angular momentum. So, or in other words, we can say that the conservation of total angular momentum is a consequence of isotropy of space, or we can say that isotropy of space leads to the conservation of angular momentum, or total angular momentum of the system remains conserved. So that's all for this lecture. In the next lecture I will talk about isotropy of time.